Hello class, today we're going to identify the functional groups in an organic molecule with 80% accuracy. We're going to identify isomers of organic compounds, and we're going to identify cis and trans geometric isomers. I love organic. I wish we could go a lot more in depth with organic. I even wish that we had an organic class here in high school. Organic is probably one of the harder topics you'll have as a first year student in college. It's typically viewed as the weed out class among a lot of biology and chemistry and pre-med majors. So I certainly hope we can have a little bit of time to dive more into organic. But for now, we're just going to cover functional groups. There will be a paper assignment dealing with functional group identification, and hopefully this just gives you a little taste of some of the stuff we need to know for organic. Okay. So one of the main things I want to talk about first is the skeletal formula or the bond line formula. Often in organic structures, we use a shorthand notation for Lewis structures because there are so many carbons and so many nitrogens, so many oxygens and hydrogens. We like to save time and be efficient. In the skeletal formula, carbon atoms are not written. We assume that the carbons are at the vertices of lines when we draw a line bond structure. So where the lines meet, here would be, for example, a carbon. We also know the terminal ends of the lines are also carbons. We're looking at butane here. We have 4 carbons. We also don't show the hydrogen atoms unless they're bonded to nitrogen or oxygen. We assume that everything bonded to carbon that's not drawn is a hydrogen. We can infer the number of bonds, or we can infer the number of hydrogens based on the number of bonds to a particular carbon atom. So, for instance, if we're looking at carbon number 1 here, carbon number 1 doesn't have anything else bonded to it that we can see, so we assume that the remainder of those bonds are hydrogens, which means because carbon can form 4 bonds in total, it's assumed that there are going to be 3 additional hydrogens sticking off of here. Okay, and that makes sense if you look over here. This is the same thing, carbon, and there are in fact the 3 hydrogens. If we're looking at carbon number 2, we know that this carbon is bonded to carbon number 2, and this carbon is bonded to carbon number 2. Since it can only form 2 additional bonds, that must mean we have 2 additional hydrogens sticking off of it. Okay, so that the fact that carbon can have up to 4 bonds in total is huge. It's a huge thing we need to know because then we can imply how many hydrogens are bonded to it from there. All right. So when we're looking at functional groups, I would memorize these functional groups. You're going to have to memorize them for college. You're going to have to memorize them for organic. Flashcards are the best way. The nomenclature of these things helps a little bit. Maybe you've seen the nomenclature before. We're not going to really focus on nomenclature here, just for the interest of time. Maybe at another point in time we can look at nomenclature if there's more time available to us. Something you do need to know, just in terms of naming though, methane, ethane, propane, and butane are the 4 special names of alkanes with carbons 1, 2, 3, and 4. When you have more than 4 carbons, we use a traditional naming system. 5 carbons would be pentane, 6 carbons would be hexane, based off of the number there. With organic, they've got these 4 special prefixes only for these organic compounds. Okay, so 1 carbon is methane, 2 carbons is ethane, 3 carbons is propane, and 4 carbons is butane. An alkane is a functional group comprised only of carbons and hydrogens. They're a hydrocarbon functional group. And the key here is that there are only single bonds between the atoms in an alkane. All right. Later on, we're going to refer to R groups. R groups are different functional groups that can be attached to an atom or to a molecule. And we refer to them as R or R prime when we're looking at specific functional groups only. Okay. So you'll notice that there are three functional groups. I wrote the title here. We have alkane, alkene, and alkyne. Since we have single bonds in alkane, what do you think an alkene is? You guessed it, an alkene is something with a double bond. If you've got a carbon-carbon double bond, it is an alkene. Okay, so here, for example, we've got our R groups listed. R just could mean a variety of different functional groups. We don't know what they are, but the thing that makes this thing an alkene is this feature here, your carbon-carbon double bond. If we're looking at triple bonds, that's an alkyne. So again, this thing makes it an alkyne. We don't know what's bonded to it, what other functional groups are there, but we know that triple bond between carbon and carbon makes it an alkyne. Okay, some examples you have are ethyne and propyne, where we've got carbon-carbon double bond, carbon-carbon double bond. All right, here are some more functional groups you need to know. An alcohol group is referring to an OH. If you have an OH tacked on to your molecule and it's bonded directly to a normal carbon, it is an alcohol functional group. If we're looking at ethanol, ethanol C2H5OH, we know that ethanol has an OH group sticking off of it. And then we've got our 5 carbons. Okay. Some of these other functional groups have very similar features. The ketone. The ketone is a carbon double bonded to an oxygen, and it has 2 R groups off of it. Now, the ketone is kind of like a sandwich, but if we looked at it, this looks like part of a key. That's how we remember that. It looks like part of a key that you would stick into the door, whereas some of these other functional groups, it's a little bit harder to memorize exactly what they are. You'll notice that an aldehyde looks like a ketone, so you've got that same C double bonded O, but the other important feature is that the carbon's directly bonded to an H. Aldehydes are terminal groups. You'll see them at the ends of molecules because this carbon's bonded to an H at the end. There's nothing else bonded to it. Whereas here in a ketone, this could be another carbon, it could be a hydrogen. Actually, it couldn't be a hydrogen. It's usually bonded to another carbon. If it's bonded to anything other than a carbon, it's not a ketone. It's likely to be an aldehyde or a carboxylic acid group. It's bonded to a nitrogen. You've got an amide. An amide, you've got this C double bond O group, and it is directly attached to nitrogen as a neighbor. We also have amine, which is similar to an amide, but there's no carbon double bonded to an oxygen. This is typically a terminal group. You've got N bonded to 2 H's. We don't need to know the different types of amines or amides. There are secondary and tertiary amides and amines, but we will discuss those more at a later point in time. For now, you just need to know if you see this part of a group, it's an amide. If you just see the N by itself with some H's on it, it would be an amine. The last one we'll see, this functional group here is an aromatic ring. Specifically, this one is benzene. Benzene is probably one of the most common things you'll have to draw when you're looking at an organic class. We know if we're looking at that line bond structure, each of these vertices is a carbon. We have double bonds in here, so each of these carbons only have the ability to form one additional bond. So we know that we actually have 6 hydrogens poking off of here. All right, and that would make it a benzene. Sometimes there are other functional groups sticking off of it, so we can refer to it as an aromatic ring. The name actually does change when you start tacking on other things, like you have an OH that's referred to as a phenyl group or a phenol group. We don't see those as often in this course, though. Okay. Ethers. Ether is an oxygen sandwich. It's oxygen just in between two R groups, whether it's usually two carbons are attached to it. Okay. We also have a thiol, which is like an ether, but it's a sulfur sandwich. And then esters. Esters are very similar to ethers, except you've got that carbon oxygen double bond sandwiching the oxygen and probably some other carbon. And then esters are also very similar to carboxylic acids, except specifically this oxygen is bonded to a hydrogen. Carboxylic acids are the main types of acids we will see in organic. There are other acid types, as such the ones you have learned. But this functional group is always going to be acidic because we have two electronegative oxygen atoms here. And those electronegative oxygen atoms will pull electrons towards themselves, making that OH bond in between very, very weak, because all the electrons will be pulled towards this side of the molecule, making this a very weak bond. And since it is weak, it is very ionizable. Hydrogen will leave fairly easily. Okay. So, in terms of functional groups, that's all we need to know, but we do need to also talk about the definitions of some key organic terms, specifically an isomer. An isomer is when we have the same formula for a compound but has different properties. It can have different properties for a variety of reasons. If we're talking structural isomers, so it has the same molecular formula but the bonds are different. So this is when we're looking at something called like a linkage isomer or a coordination sphere isomer. I'll show you some pictures of linkage isomers in a minute. We also have stereoisomers where they have the same bonds but different arrangements. So this refers to geometric isomers and optical isomers. Optical isomers means that they are optically active. We won't really focus on that too much, but I'll show you some examples of geometric and optical isomers. Okay, so the key is with isomers, there's the same formula, but we have different properties. Structural isomers have atoms arranged in a different order, whereas stereoisomers have things in a different spatial arrangement, but arranged in the same order. Okay, so a structural isomer. This is when we have ligands that are in different places. So in this example, we have a nitro isomer versus a nitrito isomer, where it's the same formula, but that nitro group is bonded to the blue nitrogen in this case on the left, and on the right, that carbon in the center is bonded to the red oxygen, and you'll see that it actually gives it slightly different color. So they are linkage isomers. The group is just attached in a different way. Okay, still the same formula, but there are different bonds occurring within the atom. So let's draw some isomers of pentane. Pentane, we know, has 5 carbons. So you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So this is the typical structure you'll see for pentane if you're looking at the line bond formula, but I'm going to go ahead and expand it out. All right, pentane. So pentane's formula is C5H12. C5H12. Okay, so this is one of the possible versions of pentane as an isomer. We also have a couple of different ways we can draw this, where it's still the same formula, but the carbons are attached in a different way. Okay, so we also have this version, where you could have a carbon attached here, like this. We still have, if you'll notice, still an isomer. We have 5 carbons still attached here, and we still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. This would be a second isomer. Actually, this one's referred to as isopentane, if you're curious about the name. And then we also have neopentane, where you've got all the carbons forming kind of this cross shape here. And each of these terminal carbons has 3 hydrogens on them. 3 times 4 gives us 12. All right, and this would be referred to as neopentane. So there are 3 different ways we can draw this. It's a little wild. Be aware that there's a separation here. The way I've drawn this, it's really hard to see. These are not bonded to each other in between. There is space in there. When we look at the 3D structure of each of these things, they do occupy a different space, even though when we draw them in 2D, it's hard to see. Okay. So we have 3 possible isomers here. They all have the same formula. It's just they are attached in different ways. So this would be structural isomers here. Okay. We also have stereoisomers. Stereoisomers are when you have the same formula, but they are arranged in a different way. They're attached in the same way to a central atom, but they're arranged differently in space. So if we're looking at this carbon as like the central point here, and we've got 2 hydrogens, or sorry, 2 chlorines. We've got 2 chlorines and 2 nitrogens. When we have a cis isomer, the same type of atom is on the same side. So both of the NH3 groups are on the right side, both of the chlorine groups are on the left side. When we have a trans isomer, the groups are on opposite sides. So I've got then NH3 groups across from each other, and then same with the chlorine groups. They are across from each other. They're all bonded to a platinum metal in the center, but they are clearly different in the way that they are arranged. Okay. So here's another example of cis and trans isomers. You're most likely going to see these when you have double bonds here. So if they're on the same side, these CH3 groups are on the same side here. They are cis, but here they are on the opposite side, so they are trans. Okay. So let's try and arrange some of these. Let's see, the first one, again, cis means they're on the same side. I've got chlorine and chlorine on the same side, and here I've got my 2 R groups on the same side. And then this one's tricky, because you can't tell what is bonded here. If we look at where the H's are, this will be a big clue. We know there are actually H's here. All right. They're just hidden because of our line bond formula. I see that the H's are on the same side. This one is actually my cis. Okay. And this one, the H's are on opposite sides, so it is my trans. Okay. There you go. All right. So stereoisomers. There are other stereoisomers besides the geometric cis-trans isomers. These are called optical isomers or enantiomers. They are mirror images of each other. So the word enantiomer stems from the term handedness. So think about your hand. You can look at a mirror image of your hand, but then if you try to superimpose it back onto itself, they're clearly different. A right hand doesn't fit into a left glove. 2 enantiomers cannot be superimposed onto each other. This is probably one of the more difficult terms to deal with and one of the more difficult concepts to grasp in organic chemistry. If I can tell you one thing that will save your life now, go online. As soon as you know you're taking organic chemistry ahead of that semester, if you have the extra $25 to do so, it'll be the best $25 you've ever spent. Get yourself a molecule kit, kind of like the ones that we used in our bonding lab. They're $29, I think. They might even be a little bit cheaper than that. But they're on Amazon. They're from Mollymod, M-O-L-Y-M-O-D, Mollymod. There's organic and inorganic kits. If you can get yourself one of those molecule kits, it will help you with this idea of stereochemistry and stereoisomers. It's the one thing I regret not doing when I was in college was getting a molecule kit, and I definitely suffered from it. So get yourself a molecule kit. Okay. All right. So some examples. One of the other things I forgot to mention when we're looking at molecule shapes, especially Lewis structures with this line bond shorthand. is that we use dashes and wedges to represent things that are sticking out of the plane in 3D space. If it's a triangle that's filled in, it is coming out of the page towards you. If it's dashes, it's coming out of the page away from you. So like in this example here, if we were to draw a mirror image, you see that these are mirror images of each other, but if I was to try and superimpose this back onto the original molecule, aka rotate it 180 degrees, I would see that this molecule actually would look something like this. We know that those OHs on this side here are coming out of the page toward us, but if we were to rotate it 180 degrees, you would actually see that they would be coming out of the page away from us. And then that CH3 would actually be coming towards us now. Okay, so they are very clearly different molecules. Actually, I even drew this on the wrong spot. I'm sorry. So if I had tried to superimpose them, you would see that they were sticking out of different ends. Okay, so these are definitely enantiomers because this possesses handedness, or the fact that when you take the mirror image, you can't flip it back onto itself. They are not the same molecule. Okay. All right, one last question. Which of the following pairs of compounds are isomers? Remember, isomers have the same formula, but may have different arrangements or different connections. Okay. Hopefully you went through and figured out the formulas for each of these. I see for A, I've got C4H10 and C4H10. Okay. Well, right away, those two are the same, which is my definition of an isomer. It has to have the same formula. So I know A is correct. If I went through and I really wanted to prove it to myself, I could see that C4H10, and then this one's C4H9. Those are not the same. This one would be C2H6O. Here you have C3H6O. So it's pretty easy to see that these are in fact different. You just have to check all of the formulas to make sure they are in fact not the same. Okay. All right, that is all for organic, and we are done this unit. Have a great day.